Hi, in this video we're going to go over section 4.8 on the two famous theorems. And we're going to discuss a little bit of something that we discussed in 4.7, and it was about the irrationality of a square root of 2. But now let's look at it from a different point of view. So before, when we were in ancient Greek times, the mathematicians believed that given to any line segments, a certain units of length could be found, so each segment will be a whole numbers of unit long. In other words, they believe that all lengths will become measurable, and they could be expressed as ratios of integers. The discovery that square root of 2 is irrational completely shatter this belief and pretty much cause a crisis in Greek mathematics. So this starts like this. We take a square and we take a couple lines of segment 1. And so by the Pythagorean theorem, we're going to end up having the diagonal is the square root of 2. So hence, we're going to have that this diagonal was going to have a square root of 2 value. But at that point, in the ancient Greek, they thought there will be integers m and n, so that the diagonal was going to be some sort of fraction of the form m over n. This will imply that the square root of 2 was going to be from that shape. But as we know, square on both sides, we find out that 2 was going to be m squared over n squared, and that will mean that a square root of 2 will be rational. But that wasn't going to be possible. We actually showed this in section 4.7 using proof by contradiction, with the idea that you assume that square root of 2 was rational. We got to the contradiction by the fact that they don't have common factors on that ratio that we initially proposed. And so it has to be rational. So the whole idea, and notice that this is going to function for most of the other square root, the square root of 3, square root of 5. You start with the idea that the root is equals to a fraction, and then you assume that it's in the lowest term, so there's no common elements. At most can be 1 or minus 1. And then what happens when you square both sides is that you're going to get that there's going to be some sort of common factor, once again, for b and a. So in here, if we square on both sides, then we can represent a square as twice b squared, and so that will mean that a square is an integer. And so if a square is an integer, then we're going to have that the square is an integer as well, and so this will mean that it will be an even integer. So in particular, one of the theorems that we proved earlier says that if n squared is even, then n is even. So we have that a is going to be even. We do end up saying, well, that will mean a is 2k, right? Because the even condition. Then we can do pretty much the same idea with b, and we end up proving that b squared is also even, or that b is even as well. And so both a and b being even means that it's going to be a factor of 2 that is common for both. But we assume that they were already on the lowest term, so they didn't have any common factors. And that was the contradiction for getting square root of 2 not to be rational. Now, this proof was important because it proved that the irrational number existed, and it showed that not all numbers could be expressed as fractions. That was over 1,000 years ago, and it's still one of the most famous proofs that we have for numerical structure. It gave birth to the irrational numbers overall. Now, this technique can be used to prove other square roots are irrational, square root of 3, square root of 5. You can attempt to use this for one of your projects if you want to, but then you have to develop the tools to actually show that this is going to happen in a similar way. Now, another common interesting theorem that we have is going to be the infinite of the primes. So we have infinite primes, and we're all the time trying to look for what is the next prime. This has application in cryptography, especially because if you have big primes, then you can use those big, large primes as some sort of key for encrypted things. So a prime number, once again, is a number that cannot be divided more than for itself on 1, and it cannot be factored as a product of two smaller positive integers. We have as prime 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and we continue. So the question that arose a long time ago was, is the set of all prime numbers infinite, or do we have a largest prime number? So this answer was given by Euclid around 300 before Christ era. And the proof is very, very elegant and simple. So if you assume that there's infinitely many prime numbers as your theorem, then you're going to start proof by contradiction. And so what you do is you assume that there's only finally many primes, and then you're going to construct a number that has a prime factor and show that prime factor cannot be a definite primes. And so that's going to lead to a contradiction. The idea behind this proof is, well, let's assume that there's only finitely many primes. So let's say that there's n primes. So you have the prime p1, p2, p3 up to pn for some integer n. We don't know how many. Could be hundreds, but n is a number, integer. Then we're going to construct a new number. That new number is going to be n, and it's going to be the multiplication of all the primes that we have plus 1. Then we're going to have that this number is clearly bigger than 1. So by our earlier theorem, n must be divisible by some prime number. This is an integer, so an integer is divisible by one prime number. This is something that we saw previously on the class. So now we know that n is going to be divisible by some prime, but because we assume that we have all the primes in our list, it gotta be one of those, right? So that prime p gotta be some pi. So it gotta be p of I for some I, and that gotta be in here. So because of that, we're gonna have a couple cases. So well, the first thing is, let's assume that pi is gonna divide n, right? So now since n is p1 up to pn plus 1, then we can just write that the multiplication up to pi, and then from pi to pn. And so what we're going to do now is we're going to write a number m that is the multiplication of all the primes except for pi. Okay? And then we're going to see n as that number m times pi plus 1. So this allows me to write n in terms of pi, another number, and 1. Now, because we have that pi is dividing n, then we need to have that n should be pi k for some integer k. But then that means that pi k is going to be equals to mpi plus 1. Or rearranging, we will have that pi times k minus m is going to be 1. But this will mean that pi is going to divide 1. And that's a contradiction, because only 1 and minus 1 will be the divisors of 1. And pi is a prime, so at least gotta be 2. So this is a contradiction here. So pretty much we reach to the fact that we cannot have finitely many primes. And we have infinite prime numbers. Okay, so this video was pretty much a cap to the part on difficult proofs here, difficult proof methods. We were checking a little bit of historical context. There's not really a lot of things that we're going to get from this section. We're not going to have particular exercises that are bigger than what we already seen in 4.7. But this is just to check up on some of the historical aspects of this, how it was constructed. The proof about the infinitely many prime numbers was constructed over 2,000 years old. And it's constructed. You have to do a bunch of different things that is not that obvious. Also, it is shown of a more complex proof. For many of the proof that I've been giving you on this class, you kind of go over 5 steps that are kind of easy and sequentially constructed, but this is a little bit more involved and it requires more steps that you get to do to construct your contradiction. So sometimes proof gets to be a little bit more complex. Now, it's always good to remember that when to use indirect proof, and the examples of this section, although don't provide a definite answer to that question, they show a little bit of the possible guidelines in that regard. So many theorems can be proved in either of those ways, but usually when both types are possible, indirect proof is going to be the harder way to do than direct proof. So always use direct proof if you can. Just only use indirect proofs when you're proving non-existence, irrationality, and the direct approach is too difficult or too unclear. Okay? So once again, try direct proof first, then indirect proofs if needed. Here, a brief mention of the two proofs that we discussed today, the square root of 2 is irrational and the infinitely many primes. They both use contradiction. And in the case of irrationality of square root of 2, they assume first that square root of 2 is rational. Then they write that fraction that they're thinking in the lowest possible term. And they ended up showing that both A and B are even, contradicting that they have the lowest terms. In the case of the infinitely many primes, the contradiction is a little bit different because it assumes that you have finitely many primes, it lists all the primes, it constructs a very particular number. This is very creative, and then it shows that that n number has a prime factor that is not in this list. So this is a much more complex proof than this one. Now, in summary, you're always going to remember that square root of 2 is an irrational, and plenty of the roots are irrational. Square root of 3, square root of 5. Not all the roots are going to be irrational, so be careful with that. And just remember that you always have infinite many primes, and the Euclid proof is one of the approach that you can go for that. Indirect proof, it is indeed a powerful method, and some of these statements that are impossible to prove directly can be proven in this way. Contradiction is going to be essential for non-insistent proofs, so it's always good to work with them. But when in doubt, make sure that you're trying direct proof first. Okay, so this is the end of chapter 4, where we're doing number theory and proof methods. But later down the line, we're going to introduce one more method that is going to be the proof by induction. But this is going to be part of the second part of the course. So we'll see that later.